with the objective of this experiment. The first one is retention time. To determine retention time of standard caffeine solution. The second one is the peak identification, which is we want to identify caffeine peak in soft drink sample, which is we use Coke and Levita for this experiment. And the last one is quantification, which is we want to determine the caffeine amount using response factor method. Next is introduction to Hplc. What is Hplc? High performance liquid chromatography, Hplc, is an advanced analytical technique used to separate, identify, and quantify components in a mixture. It operates under high pressure to push the liquid mobile phase through a stationary packed column with enabling efficient separation of compound. This method is widely regarded for its precision and effectiveness in analytical chemistry. What is the function of Hplc? The primary function of Hplc is to separate components in a mixture based on their interaction with the mobile phase and stationary phase. Its purpose extends to various applications, including pharmaceutical analysis for drug development, environmental monitoring for detecting pollutants, food quality testing to ensure the safety, and biochemical research to study complex molecular interaction. And the last one, what is the advantage of using Hplc? Hplc offers high resolution and accuracy in separating complex mixture, making it a preferred method in analytical laboratories. It has a wide application across industry and allows both quantitative and qualitative analysis. With its high sensitivity and precision, Hplc is capable of detecting minute concentration of substance, and additionally, its automation friendly ensures repeatable and reliable results, streamlining workflow in various. Next part, we will take a look at the components of Hplc. We start with the solvent reservoir, mobile phase reservoir, and filtering. The solvent reservoir serves as the storage unit for the mobile phase, which carry the sample through the system. Typically, it is a glass bottle equipped with special caps, which is a Teflon tubing, and filter to ensure the purity and contamination. Degassing is a crucial step where a purge gas, such as helium, is used to remove dissolved gases that could form bubbles, with the spudger being a common degassing tool. The mobile phase must have a low viscosity for easy flow, be of high purity, and compatible with the detection method. Be capable of dissolving the sample components and avoid chemical reaction with them. Next is pump. The pump is responsible for ensuring a consistent flow of the mobile phase through the column at high pressure. It maintains stable flow rates and prevents pulsation, which is critical for reliable analysis. There are different types of pump used in Hplc. The first one is the reciprocating pump, which is very efficient and widely used. The second one is displacement pump, which is provide steady flow for specific application. And the last one is the pneumatic pump, which is utilize compressed gas to drive the mobile phase. Each type of pump play a significant role depending on the requirement of the analysis. Next is injectors. Injectors introduce the sample into the mobile phase. There are two common injection methods. The first one is the string injection, which is a simple method that uses a self-sealing elastometric septa suitable for pressure up to 1500 psi. And the second one is the sampling loop, which is the most widely used method, capable of handling sample volume between 5 to 500 microliter. Microsample injection valves are also available for volume as low as 0.5 to 5 microliter, and this system support pressure up to 7000 psi. Sampling loop ensure precise and reproducible sample introduction, which is crucial for reliable results. Gut and analytical column. The gut column and analytical column are essential components of Hplc. The gut column, its primary function is to protect and prolong the life of the analytical column. It prevents clogging and deactivation caused by the sample contaminant and must match the internal diameter of the analytical column to maintain performance. Analytical column. This is the core component responsible for achieving separation of the sample component. It is typically made of stainless steel and has a calibrated length of 10 to 30 cm with an internal diameter of 4 to 10 mm. The column is packed with particle size to 5 to 10 micrometer to facilitate the effective separation and resolution. The detector identifies and qualifies the separated component as the elute from the column. There are two main types of detector. The first one is the bulk property detector. These respond to the property of the mobile phase, such as refractive index, dielectric constant or density. And the second one is the solute property detectors. These respond to property unique to solute, such as UV absorbance or fluorescence. In this experiment, a diode array detector is used, which measures solutes based on their UV absorbance property. This detector provides precise and reliable detection for various analytes.
Okay, we're moving to the apparatus and chemicals that we need for the Hplc experiment. For the apparatus, we need beaker, burette, glass rod, volumetric flask 100 ml, dropper, and for the chemicals is caffeine standard, soft drinks, Coke or Levita, distilled water, and acetonitrate. Okay, now we're moving to the methodology. First is caffeine standard solution. Stock solution 1.0 milligram per ml as a solution A. 10 milligram caffeine weigh into 10 ml volumetric flask and then dissolve in distilled water and then made up to volume with distilled water. Second one is working solution 0.1 milligram ml as a solution B. 1 ml solution A pipeted into 10 ml volumetric flask and made up to volume with distilled water. And next one is sample preparation. 10 ml of soft drink sample poured into small beaker. Magnetic stirrer used to remove any carbonation. And lastly, 2 to 5 ml aliquot filtered through 0.45 micrometer pore diameter membrane filter to remove particulate matter. Operation of Hplc. The mobile phase was pumped through the system at high pressure. 10 microliter of solution B was injected into Hplc to establish the retention time of caffeine. Next, the solution traveled through the column. Components separate based on their interaction with the stationary phase. And then, after separation, components are detected by the detector, producing a chromatogram that displays each component's retention time and concentration. And lastly, repeat with injecting 10 microliter of prepared soft drink sample solution into the HPLC.
Assalamualaikum warahmatullahi wabarakatuh. I will continue for the result. So as you can see, this is figure 1, which is graph for determination of caffeine in standard caffeine. So the next one is figure 2, which is graph for determination of caffeine in Coke. Last but not least, this is the graph for determination of caffeine in Levita. Next, this is the result for retention time and also peak area of caffeine. As you can see, this is the three compound, which is caffeine standard, Coke and Levita. So for the retention time, we got 2.482 for caffeine standard, meanwhile Coke is 2.481, and lastly Levita, which is 2.479. For peak area of caffeine, the caffeine standard is 6249.48779. For Coke is 7001.12305, and lastly Levita 11151.10.
Now, let's go over the data analysis for our experiment. First thing first, we need to know the retention time for our standard caffeine solution. The retention time for our standard caffeine solution is 2.482 minutes. Why do we need to know this? Well, this serves as a reference point for identification of caffeine in our sample. For example, when we take a look at our Coke sample, we can see a peak with a retention time of 2.481 minutes, which is pretty close to the reference point, that is 2.482 minutes. This prove the presence of caffeine in this sample. The same goes for Levita, which had a peak with a retention time of 2.7479 minutes, again proving the presence of caffeine in the sample. Next is the determination of caffeine amount in our sample. First, we need to find the RF, the response factor. we can get this by dividing the peak area of standard caffeine solution against the concentration of standard caffeine solution. We get the value of RF is 62.49488. From there, we can figure out the concentration of caffeine in the sample by dividing the peak area caffeine in a sample against the response factor. For Coke, we get 112.027 ppm, and for Levita, we get the value of 178.43 ppm. So ultimately, we can say that the Levita had a higher amount of coffee concentration in it compared to Coke.
To conclude, we get knowledge about high-performance liquid chromatography (HPLC) and how to use it with the right technique during experiments. After experiment being conducted, we have determined retention time of standard caffeine solution, which is 2.482 minutes, on the peak area of caffeine of 6249.48709. Other than that, we have identified caffeine peak in each of soft drink samples, which is Coke is 7001.12305 and Levita is 11151.10000. Lastly, we have calculated the amount of caffeine in each of soft drink samples using response factor methods. Using formula of response factor, amount of caffeine Coke is 112.027 ppm and Levita is 178.43 ppm.